This is the probabilistic model session, the first of the four we're having, and the kind of four components of mathematics of neuroscience for understanding intelligence computationally. What I'm going to do is I'm going to run through a blazingly fast discussion of what the probabilistic approach to modeling the mind and solving machine learning problems is. And then try to move on to where I think there are some very interesting future directions and hopefully stimulate discussion throughout the rest of the conference. Very briefly talking about some of the work that I do, but this isn't that kind of talk. Okay, so, I'm going to start with the definition, and I don't even really want anyone to read this, but if you had to define what probabilistic models were, models of the probabilistic interrelationship of different consequential variables within an environment an optimal learner should use to solve ecologically relevant computational problems. One general feature of this field is people are really explicit with their definitions, wordings, and computational models. And so I think a better way to sort of approach it is, okay, so what can probabilistic models do? And so the paradigmatic example is prediction. And I kind of hoped in my talk to give also an introduction to the computational problems of the island, and so I think, by far and away, this is the greatest challenge and has the greatest rewards on an island like Rhodes, which is, what is the probability that given a restaurant or let's say a scene, they will serve good fish to you? So I'm going to focus on prediction, but, it's worth saying that this idea of having modeling the behavior of an agent based on their beliefs can also be applied then downstream to inform actions in frameworks like reinforcement learning, which we've heard a little bit about, where the computational problem is now to take an action that maximizes the expected reward, and it's an expectation. The expectation is over the probabilistic component, essentially the hypotheses of the agent that encode the structure of the model. And I think then there's a key distinction between probabilistic models in machine learning and probabilistic models of cognition. So there's an extra claim in probabilistic models of cognition, which is that we're genuinely trying to understand at least the statistical information that humans, if they're acting optimally, should encode from a situation in order to act optimally. So back to the prediction. So really, this prediction is actually a conditional distribution, okay? And so given the data that we've observed, what probability will we put on this hypothesis that they might serve as good fish? And really, again, we're also conditioning on the background knowledge of the learning agent. And this, as we've come to see later, actually plays a great deal, a large role in how the beliefs are justified, or the structures of hypotheses that we give to agents are justified. And this is like the kind of master equation of prediction, but it's something that just falls about from the manipulation of the axioms of probability theory. And it says something like, if we were to make this conditional prediction, we should marginalize across hypotheses about the relevant structure of the world. So this is just a kind of a way to break down this computation into basically two components. This is a posterior predictive distribution, and so we're using the posterior probability of a hypothesis. So how likely is it given the data we've observed? We're using it to weight the prediction that given that hypothesis, what's the probability of our outcome? And so I'm sure that the idea of a sort of a hypothesis kind of might seem like 20th century philosophy of science, perhaps. And so I think it's quite interesting to start to break down what hypotheses mean in terms of computational models or beliefs available to the learner. So the history of probabilistic models is that they've taken, the quintessential psychological studies that were done in the 20th century and provided a unifying framework. And so going to the psychological studies of the 20th century, a lot of interesting work was done on the idea of categorization. And so one maybe initial way to approach solving a problem like this is to consider our hypotheses as latent classes or categories. So we can break this computation down in terms of given the data, given this image that we're seeing, this restaurant by the sea, what's the probability that it's a fish place given the data? And then how would that, we weight our prediction. If it's a fish place, it probably serves good fish. Whereas, is it a meat place? If it's a meat place, you probably shouldn't order fish there. And I have to say that is if you have to arrive at a restaurant in Rhodes with any single simple principle, I really recommend this one. Is it a fish place or a meat place? And order within that category. Okay. So just a kind of sense from the audience, do people think this is a fish place or a meat place? So for fish place, or hands up, and hands up for meat place. So this is where James and I had lunch yesterday. It's a fish place, yeah. What about this place? Some of you might recognize it from last night. So fish place, meat place. Good, yeah, this is excellent. This place, fish place, meat place. Yeah, it's an excellent fish place. It's quite far away. What about this place? Wow, right, fish place, meat place. This is a beach bar. Don't order food there. So what's my point? My point is that the way one would approach such a problem in, at least in these kind of traditional models of categorization, is to kind of identify a set of features that could be discrete, that could be continuous, that sort of that model the data we're seeing in scenes or in real life. So by the sea, is it clean? Are there knives, tablecloths, people eating fish, etc. And use Bayes' rule to invert the posterior distribution, what we're going to weight our prediction with, into a likelihood term. So the probability, given our hypothesis, given it's a fish place, it would have generated, this data in this particular example of a sort of distribution over these properties, weighted by the prior probability of it being a fish place, or that hypothesis. So we're on an island, so fish place is a higher probability than meat place. And traditionally these models would conduct experiments. These studies would conduct experiments and try to tease out what the different posterior probabilities people would place on different categories, and explain that in terms of the structure of that hypothesis, so the mathematical structure. So given this kind of new ambiguous place that I've never been to, the way one would actually make such a categorization is compute the likelihood under the different hypotheses. So here, I think I put fish place in blue and meat place in red, probably. And two very influential strategies that go back to, let's say, Plato and Aristotle, prototype and exemplar strategies. And so these are ways for actually computing this likelihood term. And they basically translate the idea of a distance between the distribution of features to the probability that the new image would have been generated under the old hypothesis. Okay. Exemplar strategies, so let's say, first formulated by Aristotle, would encode the categorical structure of the hypothesis in terms of the actual exemplars that have been observed. And so, it might not be too much of a stretch. So in 1995, this work by Alonso Rees related these strategies to statistical strategies for density estimation. The prototype strategy being parametric, the exemplar strategy being non-parametric. Okay, so there we go. So this is my kind of very high level, very fast introduction to probabilistic models. We've got this idea of a computational problem, something in the environment that's ecologically relevant. We've got this idea about breaking it down according to the laws of probability theory, and in particular, an emphasis on Bayesian statistics. So in this particular case, we've chosen a posterior predictive distribution. And we've got this idea of posterior distribution, very important, but using Bayes' rule, we can invert it into things that at least we can begin to structure according to the types of environment the types of information in the environment that we can encode into a model that would reasonably express someone's beliefs or a learner's beliefs. Okay, so but what do you have to do? Like, you know, that's a probabilistic model. What is going on behind the scenes? And what are the interesting components of this paradigm that we could vary, right? And so one, I'm sure, you know, this the idea of breaking nowadays, the idea of breaking the scene down into like a small set of discrete features might seem reductive, and it might seem like it might not identify the right categories even. So we call that the data. You know, as probabilistic modelers, a very important part is to specify the structure of the generative models that give rise to each member of the hypothesis space, or to specify the family of models that constitutes the hypothesis space. So in these, you know, in these categorization studies, usually Gaussian distributions or mixture of Gaussians or variations on that are used. But that's really a modeling choice. And then the background knowledge K available to the learner, again, a modeling choice. So what is the functional form of these different distributions? And usually conjugacy is used between the prior and the likelihood to derive, you know, a tractable posterior, or various other strategies are taken. We saw, you know, very briefly there, the idea of different statistical strategies for encoding the likelihood, prototype, parametric, non-parametric. And then the background knowledge of the learner is also encoded into the prior distribution itself of a hypothesis, fifth place or meet place. And now here's the thing that I kind of find the most interesting or stimulating, I've talked very briefly about it, is this idea of setting up the computational problem itself, right? Saying that this is something that humans face, this is a fair way to break it down. This is something I find very interesting. This is all up to the modeler, and there are very few accounts really of how one would automate this process, for example. But a great success in a really very wide range of empirical and machine learning studies, you know, using probabilistic models to encode your uncertainty about the environment have provided a very good account of data. So I'll run through a few. This is just from my work, but I think it kind of represents a long tradition of instead of using something like a category as a hypothesis, here we can use a theory. And a theory is meant in an intuitive folk sense that kind of encodes that tries to explain the interactions of different objects, these blocks, whether they line up next to each other or not, in terms of their latent class and in terms of relational stochastic structures between latent classes. That's called a stochastic block model. You know, there are these very interesting experiments about causality that these models can provide good accounts of, you know, experimental behavior, also tracking and causality in this kind of slightly different counterfactual physical intuition, and so on. And so really a realm of great success. However, you know, I think, as you might have seen from the examples on the screen there, all of these studies are conducted in these highly artificial laboratory settings typical of 20th century psychology. And, you know, now we're in the 21st century. What about the future? Could we, you know, for example, is it straightforward to generalize those findings to the type of noisy, ambiguous, lifelong learning that someone like a group fisherman would go through? It arguably contains all of these components, but it seems like a very far stretch to generalize from the lab to that sort of setting. And so I think that there are all of these components are components with which we could vary in order to try to approach more naturalistic settings and to approach more naturalistic learning problems. So one is a representation of data, for example. One's a representation of hypotheses, and there's been a lot of work, you know, these in the real world, to specify these hypothesis spaces fully considers very intractable, very large classes of problem. You know, is it really even the case that we can think about the problem in this way? The background knowledge and also the question, you know. And so very briefly, I've done a little bit of work on trying to make these models, you know, more applicable to naturalistic settings. And so the first setting is in the idea of categorization. These were the typical stimuli that were used in categorization studies that can typically be represented using kind of two latent dimensions. You know. I've been in the past, and in some follow-up work along with Ilya, we've been working on how to extend these models to naturalistic images, and in particular the idea of using deep neural networks now to encode the data. And we kind of find that actually all of these previous work had focused on the categorization strategy being the important computational question. And I think what might be obvious now is that we find that the method used to learn or extract the features is far more influential in how well you can predict human decisions and inform machine behavior. Okay. Then there's this other kind of naturalistic setting I've been thinking of, which is like island hopping in the Greek islands. So you might not have been in Rhodes before, but you come with very strong analogies from other islands that you've been to. How can we start to move towards this more naturalistic setting of lifelong learning and generalizing from different analogical bases? And so in the kind of toy example here, I've done a little bit of work exposing people to different consequential relational structures across trajectories of experiments and see how that affects their generalizations, 0 shot, 1 shot. And it affects them very strongly, maybe unsurprisingly, but has not been captured in any previous experimental work. Okay, so this is the kind of, I think these are kind of 2 Greek islands. This is the island of Skye, and this is Koh Tao in Thailand. And I think there are probably good relational theories you can learn of each of them that generalize to Rhodes. So then kind of more deeply, there's this idea of where did I conjure up these hypotheses from? Why was that an accurate framing of the problem? And Ishita, who was going to give a talk, but regrettably, because of visa issues, could not come. She's done a lot of fascinating work on where did these hypotheses come from. This is a sort of algorithmic level explanation. We're also going to hear from Bill shortly, very, very soon, in fact. And one idea from computational cognitive science is to think about chains of people, so advice between people as revealing the underlying prior beliefs of the population. So iterated learning, where maybe, one person in the chain would be revealing something like the posterior distribution given a particular point of data, the next person resampling. Well, there's also a sense in which hypotheses at this different level of analysis, the suggestion of hypotheses themselves could come through chains of people or through culture. We're going to hear about that very shortly, I think. Right, Bill? Excellent. But yeah, I've been thinking about this problem, basically. Where do good problems come from? And so I saw one of my friends send me this the other day, and it's like, this is a sort of modern AI take, I think. And there's a sense in which if a very general reinforcement learning problem has been defined over some very general data, the idea that possibly any intelligent agent would come up with sub-problems along the way in order to structure their understanding and solve the final problem. And so in this example, they seeded like a startup environment with loads of chatbots and got them to like make a product. The details were really hazy, so I think they baked a lot of stuff in. But something to me is slightly unsatisfying about this, and I kind of think that just having that very broad level conception of sub-problems, coming up as a final optimization strategy towards some very general ones, we'll probably miss out on the types of seminal discoveries that we've been used to learning about in science. Okay, so I don't think Lavoisier wasn't coming up with particular sub-problems on his way to doing things. He was being genuinely creative. So at the moment, he and Sam Gershman are writing a sort of computational monograph on Lavoisier and his discoveries at the birth of chemistry. Nancy Nersessian has done very interesting work on discoveries and creativity in science and coming up with problems and sub-problems for Maxwell, also based on Faraday's work, and Darden on Mendel's work in genetics. And so I'll give you just a kind of rough example of what I'm working on and what I think is an interesting way to think about coming up with a problem. And that's something like, this is an experiment, a think aloud study, where participants are asked, okay, you have to roll this ball up the hill. If you push parallel to the slope at point Y or at point X, which will be easier? What's your confidence and why? And what's the justification? And so people will give an answer very easily, express low confidence, and then think aloud and work through what they, how they're reasoning about it. So this is one participant. They kind of reason that, okay, well, they don't really know how to push a ball up the hill. how to think about doing that, but they do know about the sort of different pressures you have to exert on a lever. Okay, but within this sort of thinking aloud narrative, they identify a new aspect or a constraint of the problem itself. And they say, okay, well, what they hadn't really thought about before is the fulcrum of a ball is in the middle. That was the difference with the initial model they provided. The fulcrum of the lever is at the base. So something through this trajectory of model proposition, generic abstraction, and learning more about the problem could be a pathway, a computational pathway for understanding really where discoveries come from and maybe problems. Okay, so thank you to Tom, my PhD supervisor, to Sam, who's now my postdoc supervisor, all the collaborators, including Ilya. And